What if everything we think we know about the universe is just the surface of something far stranger, beneath the stars, beyond the galaxies, hidden in the fabric of space itself? There might be structures so bizarre, so unimaginable, that they rewrite the rules of reality as we understand them. Picture this, a cosmic web stretching across billions of light years, invisible threads connecting galaxies like beads on a string, or dimensions curled so tightly we can't even perceive them. These aren't just wild ideas, they're serious theories backed by some of the brightest minds in science, and they're shaking the foundations of physics. The universe has always been full of mysteries, but what if the biggest ones aren't the distant black holes or the faint glow of the cosmic microwave background? What if the real enigmas are hidden in plain sight, woven into the very structure of reality itself? From dark matter shaping the cosmos like an unseen hand to the possibility of parallel universes bumping against our own, these theories push the limits of our imagination. And the craziest part, we might be on the verge of uncovering them. This is where the adventure begins. Over the next few minutes, we're going to dive deep into the most mind-bending ideas about the universe's hidden architecture. Theories that sound like science fiction but could be science fact. We'll explore how empty space might not be empty at all, how time itself could be an illusion, and why the cosmos might be far weirder than we ever dreamed. So buckle up, because what you're about to hear will change the way you see everything. The universe isn't just vast, it's alive with secrets, and we're just starting to crack them open. Let's start with the first and perhaps most breathtaking theory, the cosmic web. Picture the universe not as a random scattering of galaxies, but as an intricate, sprawling network, more like neurons in a brain or veins in a leaf. This is the cosmic web, the hidden skeleton of the cosmos, where galaxies aren't just floating alone but are connected by vast, thread-like filaments of dark matter and gas, stretching across billions of light years. These filaments are the highways of the universe, with galaxies clustered at their intersections like glittering cities, while between them lie enormous voids, regions so empty they'd make the deepest parts of space seem crowded. What's truly mind-blowing is how this web shapes everything we see. Dark matter, invisible and mysterious, acts like the unseen hand sculpting this structure. Though we can't see it directly, its gravity pulls ordinary matter into these vast filaments, guiding where galaxies form and how they move. Without it, the universe might just be a dull, uniform haze. Instead, we have this dazzling cosmic tapestry where every galaxy, every star is part of something far grander. But here's where it gets even stranger. This web isn't static. It's alive with motion, with galaxies flowing along these filaments like water through rivers, drawn toward massive clusters where gravity is strongest. These clusters, cosmic metropolises, can contain thousands of galaxies, all bound together in a delicate dance. And the voids, they're not just empty space but dynamic regions where the very fabric of the universe expands faster, tugging at the web like an invisible force. The implications are profound. This structure tells the story of how the universe evolved from a near-uniform soup after the Big Bang into the complex, interconnected cosmos we see today. It hints at the laws of physics operating on scales so vast they bend the mind. And perhaps most tantalizing of all, it suggests that what we see, the stars, the galaxies, is just the visible tip of an invisible iceberg, with dark matter and dark energy pulling the strings behind the scenes. So when you look up at the night sky, remember, you're not just seeing isolated points of light. You're glimpsing one tiny part of an immeasurable web, a structure so vast and ancient it makes our entire galaxy feel like a single thread in the grandest tapestry imaginable. Now imagine if the entire universe were being held together by something we can't even see. That's exactly what dark matter does, an invisible force sculpting the cosmos from behind the scenes. Think of it like the steel beams inside a skyscraper. You never see them, but without them, the whole structure would collapse. Dark matter works the same way. It's gravity weaving the cosmic web, pulling galaxies into position and keeping the universe from flying apart. What makes dark matter so baffling is that it doesn't behave like anything we're familiar with. It doesn't emit light, reflect it, or even interact with ordinary matter in any way except through gravity. If you stretched out your hand, trillions of dark matter particles might be passing through it right now, completely undetectable. Yet despite its ghostly nature, its fingerprints are everywhere. When astronomers measure how galaxies spin, they find stars orbiting so fast that, by all rights, they should fling themselves into space. But something unseen, dark matter, holds them in place with an extra gravitational grip. The hunt for dark matter has become one of the greatest detective stories in science. Researchers have built detectors deep underground, shielded from cosmic rays, hoping to catch a fleeting interaction. They've scanned the skies for distortions in starlight, looking for signs of dark matter bending space itself, and they've run supercomputer simulations tracing its influence over billions of years. Yet for all that effort, dark matter remains elusive, slipping through every net we cast. The stakes couldn't be higher. If dark matter exists and the evidence is overwhelming that it does, it means we're missing something fundamental about reality. Some theories suggest it could be made of undiscovered particles, relics from the Big Bang left to drift through the cosmos. Others propose that we've got gravity itself wrong, that our equations need rewriting on cosmic scales. Whatever the answer, solving the dark matter mystery wouldn't just fill a gap in our knowledge, it would redefine physics itself. So next time you gaze at the stars, consider this: what you see is only a fraction of the story. Behind every galaxy, every nebula, every flicker of light, there's an unseen architect shaping the universe. And somewhere out there, hidden in the darkness, the truth is waiting. Just when we thought the universe couldn't get any more mysterious, along comes dark energy, an even more baffling phenomenon than dark matter. While dark matter pulls the cosmos together with gravity, dark energy does the opposite. It pushes everything apart, accelerating the expansion of space itself. Imagine blowing up a balloon with tiny dots on its surface, but instead of slowing down as it inflates, the balloon starts expanding faster and faster. That's what our universe is doing right now, and dark energy is the strange force behind it. What makes dark energy so perplexing is that it seems to be a property of empty space itself. Unlike matter or radiation, which dilute as the universe expands, dark energy maintains a constant density. This means as space grows, there's effectively more dark energy driving the expansion, a runaway effect with staggering consequences. If this continues, galaxies beyond our local group will eventually be pulled so far away that their light will never reach us. The universe will grow cold, dark, and eerily empty as cosmic structures are torn apart by this relentless stretching of space. We first stumbled onto dark energy in the late 1990s when astronomers observing distant supernova made a shocking discovery. These exploding stars appeared fainter than expected, meaning they were farther away than they should have been. The only explanation, the expansion of the universe, wasn't slowing down due to gravity as everyone assumed. It was speeding up. This revelation turned cosmology upside down, forcing us to confront the unsettling truth that roughly 68% of the universe's energy is this unknown repulsive force. The battle between dark energy and gravity is shaping the fate of everything. On the grandest scales, dark energy wins, stretching the cosmic web thin, evaporating galaxy clusters, and eventually isolating islands of matter. But locally, gravity still dominates, keeping galaxies and solar systems bound together. For now, some theories suggest dark energy's strength could change over time, potentially ripping apart atoms in a catastrophic Big Rip scenario billions of years from now. Others propose it might fade away, allowing gravity to eventually pull everything back together. What's truly humbling is how little we understand about this force that controls the universe's destiny. Is dark energy Einstein's cosmological constant, an inherent energy of space itself, or is it something more exotic, like a dynamic field evolving over time? Every telescope we build, every supercomputer simulation we run brings us closer to answers, but the mystery endures. One thing's certain: in the grand tug of war between dark energy and gravity, the fate of all cosmic structures hangs in the balance, and we're just beginning to grasp the rules of the game. What if our universe isn't the only one? The multiverse hypothesis suggests that beyond the edges of our cosmic horizon, there could be countless other universes, each with its own laws of physics, its own versions of stars and galaxies, even its own versions of you. This isn't just science fiction. It's a serious scientific idea that emerges from some of the most advanced theories in physics. And if it's true, the structures connecting these universes might be hidden in the very fabric of reality itself. Take string theory, for example. At its core, this framework proposes that the fundamental building blocks of the universe aren't point-like particles but tiny, vibrating strings. These strings twist and resonate through higher dimensions we can't perceive, curled up so tightly they're invisible to us. In some versions of string theory, these hidden dimensions could be the bridges between universes, like threads stitching together separate patches of a vast cosmic quilt. Each universe might sit on its own brane, a membrane-like surface floating in a higher dimensional space, occasionally brushing against others in ways that could leave faint imprints in the cosmos. Then there's the bubble universe concept. Imagine the multiverse as an endless sea of foam, where each bubble is a self-contained universe inflating from its own Big Bang. Our universe is just one bubble among countless others, each with its own unique physics. Some might have stronger gravity, others might have no stars at all, and a few could even harbor alien civilizations asking the same questions we are. The mind-bending part: these bubbles might collide or merge, leaving scars in the cosmic microwave background, subtle fingerprints of a reality far bigger than our own. But how could hidden structures connect these worlds? Some theories suggest quantum entanglement, the eerie link between particles across vast distances, might extend beyond our universe, tying parallel realities together in a web of invisible connections. Others propose that black holes could be portals, their singularities warping space-time so intensely that they puncture through to other universes. And if even one of these ideas is correct, it means the universe we see is just a single page in an infinite cosmic library. The implications are staggering. If the multiverse exists, it could explain why our universe seems so finely tuned for life. Maybe we're just one of countless variations, a lucky roll of the dice in a cosmic casino where every possible outcome plays out somewhere. Or perhaps these parallel worlds are so different that our laws of physics are just one strange possibility among an endless spectrum of realities. Either way, the multiverse hypothesis forces us to confront the humbling possibility that everything we know might be just a tiny sliver of a much grander, far stranger whole. At the smallest scales imaginable, where even atoms seem gigantic, space itself might be seething with chaos, a turbulent, bubbling ocean known as quantum foam. Picture the surface of a boiling pot, but instead of water, it's the fabric of reality that's constantly churning, with tiny regions of space and time popping in and out of existence. These fleeting fluctuations are so small they'd make a grain of sand look like a planet. Yet they could hold the key to understanding the universe's most fundamental structure. This idea emerged from quantum mechanics, which tells us that empty space isn't truly empty. Even in a perfect vacuum, particles and antiparticles flicker into being for unimaginably short moments before annihilating each other, a phenomenon called quantum fluctuations. But zoom in even further, and space-time itself might be unstable, warping and twisting at scales a trillion times smaller than an atomic nucleus. In this realm, the smooth, continuous space we're familiar with could dissolve into a frothy, ever-changing mess where the very concepts of here and now lose their meaning. What's truly wild is how these microscopic tremors might echo across the cosmos. Some theories suggest that quantum foam could leave faint imprints on light traveling billions of light years, subtly distorting its path like ripples in a pond. Others propose that these fluctuations might have seeded the universe's largest structures, those cosmic web filaments and galaxy clusters, by amplifying tiny density variations in the early universe. It's as if the universe's blueprint was written in the frenzy of its smallest possible scales. The implications get even stranger when you consider black holes. Near a singularity where gravity warps space-time to its breaking point, quantum foam might become so extreme that it opens microscopic wormholes, brief tunnels connecting distant points in space or even different universes. These wouldn't be the sci-fi kind you could fly a ship through. They'd be vanishingly small, lasting for fractions of a second. But their existence would mean that beneath the apparent order of the cosmos, space-time is fundamentally unstable, riddled with shortcuts and tiers we can't yet detect. Of course, we can't observe quantum foam directly. Its scales are far beyond even our most powerful particle colliders. But experiments like gravitational wave detectors might someday catch whispers of its effects, and theories like loop quantum gravity are already reimagining space-time as a network of interconnected threads rather than a smooth sheet. If they're right, reality might be more like a woven tapestry, with every twist and knot in the fabric shaping the universe we see. So the next time you stare into the night sky, remember, the vast, serene cosmos might just be the calm surface of something far more turbulent. Beneath every galaxy, every star, even every atom, there could be an unseen storm raging, a quantum sea frothing with possibilities, quietly sculpting the universe from the shadows. What if the universe had secret tunnels, hidden passageways that could let us leap across billions of light years in an instant? That's the tantalizing promise of wormholes, cosmic shortcuts theorized to bend space-time so drastically that two distant points become neighbors. Imagine folding a piece of paper so the edges touch. A wormhole would be like poking a pencil through the fold, creating a bridge between places that would otherwise take eons to reach. These hypothetical structures aren't just sci-fi fantasies. They emerge straight from Einstein's equations of general relativity, where gravity warps space-time so intensely that it could stitch together far-flung corners of the cosmos. But here's the catch: wormholes, if they exist, would be incredibly unstable. According to the math, they'd snap shut the moment anything tried to pass through, unless some exotic form of matter or energy could prop them open. Think of it like trying to hold a tunnel open against a collapsing ceiling, but instead of steel beams, you'd need something with negative energy, a substance that repels gravity itself. Quantum physics hints that such weird materials might exist, bubbling up from the froth of empty space, but harnessing them is another matter entirely. Detecting wormholes is even trickier. Unlike black holes, which announce themselves with swirling gas and gravitational waves, wormholes might leave only faint clues, subtle distortions in starlight or strange patterns in the cosmic microwave background. Some scientists have suggested looking for ghost images of galaxies that appear duplicated due to light bending through a wormhole's throat. Others propose that colliding black holes might momentarily unveil hidden passages if their singularities connect across space-time. The implications, though, are staggering. A stable wormhole could revolutionize space travel, turning journeys that would take millennia into afternoon strolls. It might even offer a backdoor to parallel universes if certain string theory models hold true. But the biggest revelation would be what wormholes say about space itself, that the universe isn't just vast but deeply interconnected, threaded with invisible seams we're only beginning to imagine. So while we haven't found one yet, the search reshapes how we see the cosmos. Every unexplained warp in space, every odd gravitational signal, might be a whisper of these cosmic shortcuts waiting to be uncovered if we know where to look. Black holes aren't just cosmic vacuum cleaners, they might be the universe's most sophisticated hard drives, storing information in ways we're only beginning to understand. The black hole information paradox is one of the most heated debates in physics, challenging everything we know about reality. It starts with a simple question: when something falls into a black hole, where does its information go? According to quantum mechanics, information can never be destroyed. It might change form, but it's always preserved. But black holes, with their crushing gravity and event horizons, seem to break that rule. If you toss a book into one, all the words, the ink, even the atoms themselves appear to vanish forever. So does the information inside that book just disappear? This puzzle has divided physicists for decades. On one side, Stephen Hawking famously argued that black holes slowly evaporate over eons, radiating away their energy in a faint glow we now call Hawking radiation. But if that's all that's left, where did the information go? It's like burning a library and claiming the smoke contains every word from every book. The math suggests it's impossible, yet Hawking's calculations seem to show it happening. This contradiction is the heart of the paradox, and solving it could rewrite the rules of quantum mechanics and gravity. Enter the holographic principle, a radical idea suggesting that all the information swallowed by a black hole isn't lost, it's encoded on its surface. Think of it like a cosmic projector, a two-dimensional event horizon holding all the data of the three-dimensional objects that fell inside. It's as if the universe compresses information into a shadowy film, preserving it in a form we don't yet understand. This theory implies that black holes might be the ultimate archivists, storing the universe's secrets in a language written in gravity and quantum bits. But the debate doesn't stop there. Some researchers propose that black holes don't destroy information. They scramble it like a cosmic blender, turning matter into an unrecognizable quantum soup before spitting it back out as Hawking radiation. Others suggest that black holes might not have interiors at all, that their insides are just illusions created by tangled space-time. And then there's the wild card, wormholes. If information slips through hidden tunnels to other universes or distant parts of our own, it could mean black holes are less like endpoints and more like revolving doors in the fabric of reality. What's at stake isn't just academic, it's the foundation of physics itself. If information can vanish, our understanding of cause and effect crumbles. But if it's preserved in some exotic form, it hints at a deeper layer of cosmic structure, a hidden code woven into the universe's architecture. Every experiment, from gravitational wave detectors to quantum computers, brings us closer to an answer. And when we find it, we might not just solve a paradox, we could uncover the universe's ultimate filing system, where every event, every particle, is meticulously recorded in the dark heart of a black hole. What if our three-dimensional reality is nothing more than an illusion, a holographic projection from a two-dimensional surface at the edge of the universe? This isn't the plot of a sci-fi movie, it's the holographic principle, a theory so radical it turns our understanding of space, time, and information upside down. Imagine watching a movie on a flat screen. Every explosion, every gust of wind, every tear on an actor's face is just pixels arranged in a way that tricks your brain into seeing depth. Now apply that to the cosmos. The stars, planets, even your own hands might just be incredibly detailed projections from a hidden 2D layer encoding all the information in the universe. The idea sprouted from an unexpected place: black holes. When physicists realized that the maximum entropy a black hole can contain isn't proportional to its volume but to the area of its event horizon, it flipped intuition on its head. Normally, you'd expect more space to mean more room for information, like a bigger hard drive. but black holes suggest that all the data describing what's inside them could be plastered on their surfaces like a cosmic barcode. The holographic principle takes this further, proposing that the entire universe might work the same way. All the events, particles, and forces we experience in 3D could be shadows cast by information etched onto a distant 2D boundary we can't see. If true, this means dimensions themselves might not be fundamental. The 3D world we move through could emerge from interactions on a flat surface, the way a 3D video game is ultimately just code running on a 2D chip. Even stranger, it implies that space isn't smooth and continuous but pixelated at the tiniest scales, like a digital image zoomed in too far. These pixels of space-time would be unimaginably small, trillions of times tinier than an atom. But if you could peer deep enough, you might catch reality glitching like a low-resolution screen. The implications ripple through every corner of physics. Gravity, quantum mechanics, even the nature of time could all be side effects of this holographic translation. Some versions of string theory already suggest that our universe is a membrane floating in higher dimensional space, with the holographic principle acting as a kind of cosmic compression algorithm. Others speculate that black holes might be bridges between the 2D code and our 3D reality, funneling information from one layer to another. But how could we ever test such a mind-bending idea? Surprisingly, there are clues. Scientists have looked for signs of this pixelation in the cosmic microwave background, the afterglow of the Big Bang, searching for telltale blurs that might reveal space's underlying graininess. Particle accelerators might someday probe tiny enough scales to catch reality, buffering, and anomalies in quantum entanglement could hint at hidden layers encoding our 3D world. The holographic principle forces us to confront a humbling possibility that everything we see, touch, and experience might be the universe's grandest illusion, a shadow play cast by something far simpler and far stranger, lurking just beyond the edges of perception. If that's true, then the search for the universe's hidden structure isn't just about mapping galaxies or particles. It's about deciphering the ultimate cosmic code, written in 2 dimensions but unfolding into everything we know. Imagine the universe not as an island floating in nothingness, but as a sheet of paper drifting through a vast, unseen dimension. This is the heart of brane cosmology, the idea that our entire cosmos might be a 3-dimensional membrane or brane, adrift in a higher dimensional space beyond our perception. These extra dimensions wouldn't be like the ones we know. They could be curled up impossibly tight or stretched beyond our observational reach. But if they exist, they could rewrite our understanding of reality's very foundation. The most striking implication, the Big Bang might not have been the beginning of everything, just a collision. Picture 2 of these branes floating in a higher dimensional bulk, slowly drawing closer over eons. When they finally meet, the impact could unleash enough energy to birth an entire universe, seeding matter, radiation, and the very fabric of space-time in an instant. It's like clapping your hands together and creating a storm of galaxies in the shockwave. This ekpyrotic model offers a breathtaking alternative to the classic Big Bang narrative, suggesting our universe emerged not from a singularity but from a cosmic accident in a hidden dimensional arena. But how could something so vast come from a collision? The math reveals something extraordinary. When branes collide, their energy doesn't just dissipate, it concentrates along their surfaces, igniting a fireball of particles and forces confined to the brane itself. To us, trapped within our 3-dimensional slice of reality, this would look like an explosion of incomprehensible energy, the Big Bang. And because the higher dimensions remain invisible, we'd never see the neighboring brane that started it all. This theory also solves one of cosmology's biggest puzzles: why the universe is so uniform. In the classic Big Bang model, distant regions of space shouldn't have had time to reach the same temperature, yet the cosmic microwave background shows an eerie evenness. Brane cosmology offers an elegant fix. Before the collision, the branes could have been stretched smooth over unimaginable distances, meaning their impact would imprint that smoothness onto our newborn universe. It's like pressing two perfectly flat sheets of glass together. The resulting pattern inherits their flawless alignment. The echoes of this collision might still be detectable today. Some models predict that the brane smash would have sent ripples through space-time gravitational waves with unique signatures hiding in the universe's oldest light. Others suggest that if our brane occasionally wrinkles or vibrates in the higher dimensional bulk, it could explain dark energy's mysterious push on the cosmos. Even the oddities of quantum mechanics might trace back to particles being subtly influenced by their higher dimensional surroundings, like shadows flickering on a cave wall. Of course, brane cosmology isn't without its challenges. We've yet to find direct evidence of extra dimensions or brane collisions, though experiments like the Large Hadron Collider continue hunting for clues. And if branes exist, what else shares their hidden realm? Could other universes, each with their own physics, float just a dimensional whisper away? The beauty of this idea lies in its audacity. It dares us to think beyond the confines of our senses, to envision a reality where the universe's grandest structures are just fragments of something far larger. If branes are real, then the Big Bang wasn't the beginning. It was just the moment our tiny slice of existence blinked into view, one page in a story written across dimensions we're only beginning to dream of. What if the universe doesn't end with a cold, dark fade-out, but with a rebound, bouncing back like a cosmic rubber band? This is the core of the Big Bounce theory, a radical reimagining of the universe's fate where expansion and contraction repeat in an endless cycle. Instead of a one-time Big Bang, this model suggests our universe might be just the latest chapter in an infinite series, each ending with a collapse so extreme it sparks a new beginning. Hidden beneath this dizzying loop could be structures that survive the chaos, threading through each cycle like echoes of a deeper cosmic order. Picture the universe not as a single, linear story, but as a phoenix perpetually rising from its own ashes. According to the Big Bounce model, when dark energy's outward push weakens, gravity begins pulling everything back together. Galaxies merge, space contracts, and temperatures soar until all matter and energy crush into an unfathomably dense state. But instead of ending there, quantum effects trigger a rebound. The collapse reverses in a violent surge, birthing a new universe from the remnants of the old. It's as if the cosmos takes a deep breath, holds it, and exhales into a fresh expansion. The most tantalizing part, certain structures might endure these apocalyptic transitions. Just as ice crystals retain patterns when water freezes and melts, the universe could preserve hidden imprints across cycles. Some theories propose that the cosmic web's filamentary scaffolding, the vast network of dark matter and galaxies, might re-emerge in similar configurations like a recurring blueprint. Others speculate that fundamental constants, like the strength of gravity or the mass of particles, could carry over, subtly tuned by each bounce to allow complexity and life to arise again and again. Clues might already be hiding in plain sight. If previous cycles left faint scars in the cosmic microwave background, anomalies in temperature or polarization, they could serve as cosmic fingerprints. Some researchers even suggest that black holes, those enigmatic traps of gravity, might not fully evaporate between cycles. Their information could encode remnants of past universes, leaking into the new one like messages in a bottle. Of course, the Big Bounce isn't without controversy. Critics argue that entropy, the universe's tendency toward disorder, should accumulate with each cycle, making successive universes increasingly chaotic. Yet proponents counter that quantum effects or undiscovered physics could reset entropy during the bounce, like shaking a snow globe to redistribute the flakes. The debate hinges on mysteries we're still unraveling, from quantum gravity's rules to the true nature of the singularity. What makes this theory so compelling is how it reframes our place in the cosmos. If the universe cycles endlessly, then beginnings and endings are illusions, just phases in an eternal rhythm. The stars above us might have burned countless times before, and the atoms in our bodies could have been part of civilizations long forgotten. It's a humbling thought that the universe's hidden structures might not just shape space but time itself, weaving a tapestry grander than we've dared to imagine. What if everything around you, the stars, the trees, even the device you're using right now, weren't real? Not in the philosophical sense, but literally, a hyper-detailed simulation running on some unfathomable computer. This is the simulation hypothesis, a theory that's equal parts thrilling and unsettling. It suggests our universe might be nothing more than lines of code in an advanced civilization's cosmic program, with every law of physics just a carefully crafted algorithm. The idea isn't new. Philosophers like Descartes toyed with it centuries ago, but today it's gained traction with scientists, tech billionaires, and even Nobel laureates debating its plausibility. At its core, the argument hinges on probability. If civilizations eventually develop the power to create simulations indistinguishable from reality, and if they run countless versions of them, the odds tilt heavily toward us being in one of those simulations rather than the original universe. Think of it like video games. Future civilizations might not just play them, they could live inside them with conscious beings unaware they're digital constructs. The math is seductive, but the evidence is murkier. Some theorists point to glitches in quantum mechanics, like the way particles behave differently when observed, as potential signs of computational shortcuts. Others argue that the universe's pixelated nature at the tiniest scales, Planck length, could hint at an underlying code, yet skeptics fire back. If we're in a simulation, where's the lag? Where are the rendering errors when galaxies collide? A perfect simulation would leave no traces, making the hypothesis unfalsifiable, and therefore, some say, unscientific. But the debate isn't just about physics, it's about the nature of reality itself. If the simulation hypothesis is true, it reshapes everything from free will to mortality. Are our choices our own or just predetermined outputs? Is death merely a shutdown sequence? And if the simulators exist, are they gods, scientists, or something beyond our comprehension? The ethical implications are just as dizzying. If we someday create simulations with conscious beings, do we have a moral obligation to them? Would turning off such a program be genocide? The hypothesis forces us to confront uncomfortable questions about our own potential role, not as players, but as programmers of future realities. Whether you find the idea terrifying or exhilarating, one thing's certain: it stretches the imagination to its limits. The universe might be stranger than we've dared to dream, not because it's infinite or multidimensional, but because it could be someone else's experiment, an idea that turns the search for meaning into the ultimate cosmic detective story. The ekpyrotic universe theory throws out the idea of a singular explosive beginning instead. It paints a picture of a cosmos born from collision, like two sheets of glass smashing together in some unseen dimension. Here, our universe isn't the result of a lone fireball, but the aftermath of a cataclysmic encounter between two three-dimensional membranes floating in a higher dimensional space we can't perceive. Think of it like ripples spreading across a pond after two pebbles strike the surface, except the ripples are galaxies, and the pond is all of reality. This idea doesn't just replace the Big Bang with a cooler-sounding event. It solves some of cosmology's biggest puzzles. For one, it explains why the universe is so eerily uniform. In the classic Big Bang model, distant regions of space shouldn't have had time to exchange heat or information, yet they're nearly identical in temperature. The ekpyrotic model fixes this by proposing the branes were stretched smooth before the collision, like pulling a wrinkled sheet taut. When they finally crashed, that smoothness transferred to our newborn universe, imprinting uniformity from the start. But the real magic lies in the hidden dimensions. These branes don't float in empty space, they exist in a higher dimensional bulk, a realm beyond our perception where gravity might leak between worlds. This could explain why gravity is so weak compared to other forces. It's not confined to our brain like light or matter are. Some of its influence might be bleeding into the bulk, diluting its strength in our dimension. It's like trying to hear a whisper in a vast cathedral. Most of the sound gets lost in the space around you. The theory also makes startling predictions about cosmic structure. Unlike the Big Bang's quantum fluctuations, which would create random density variations, the ekpyrotic model suggests the universe's large-scale patterns, those vast filaments and voids of the cosmic web, might bear the imprint of the brane's pre-collision vibrations. These wouldn't be tiny quantum jitters, but massive, rhythmic waves, like the slow undulations of a trampoline before it struck. If we could map the universe's oldest light with enough precision, we might spot subtle asymmetries or preferred directions, ghostly echoes of that primordial collision. Critics argue the model has gaps, like explaining what triggered the branes to collide or how they avoided shredding apart during impact. But supporters counter that it elegantly sidesteps the need for a singularity, a point of infinite density where physics breaks down. Instead of a universe erupting from nothingness, we get one rebounding from a structured, higher dimensional event. The implications are profound. If the ekpyrotic model is right, our universe might have neighbors, other branes drifting in the bulk, each with their own physics, their own stars, even their own versions of us. Some could be separated by less than a millimeter in the higher dimensions, yet remain forever out of reach. And if branes can collide once, they might do it again, hinting at a cyclical cosmos where universes are born, evolve, and merge in an endless dance across dimensions we're only beginning to imagine. What if the universe isn't just vast, but endlessly repeating? Fractal cosmology proposes that the cosmos is built like a kaleidoscope, a single, infinite pattern repeating at every scale, from the tiniest quantum fluctuations to the grand sweep of galaxy clusters. Imagine zooming into a fern leaf and finding its branching structure mirrored in the veins of a leaflet, then again in the microscopic cells. Now apply that to the universe, galaxies grouped into clusters, those clusters forming superclusters, and those superclusters weaving into filaments that stretch across billions of light years, all echoing the same basic design. It's a vision of cosmic recursion where the universe's architecture has no true bottom or top, just layers of self-similarity. This idea isn't just poetic, it has serious scientific roots. In the 1970s, mathematician Benoit Mandelbrot first formalized fractal geometry, showing how rough, fragmented shapes like coastlines or clouds could repeat their patterns infinitely when magnified. Some cosmologists, like Luciano Pietranero, later argued that galaxy distributions follow the same logic. Surveys seem to show clusters nested within larger clusters, with no clear cutoff where the pattern smooths out. Unlike the standard model where the universe becomes homogeneous at large scales, a uniform soup of matter fractal cosmology suggests the cosmos stays lumpy no matter how far you zoom out. But here's where the controversy ignites. Critics point to the cosmic microwave background, the afterglow of the Big Bang, which appears remarkably smooth at large scales. This uniformity is a cornerstone of modern cosmology, supporting the idea that the early universe was homogeneous before gravity sculpted it into today's web-like structure. If the universe were truly fractal, they argue, the microwave background would show far more variation. Proponents counter that our observations might be limited, like a person stranded on a single beach grain trying to map the entire shore. We've only mapped a fraction of the observable universe in detail, and deeper surveys could reveal larger repetitions we've missed. The debate isn't just academic. If the universe is fractal, it challenges our understanding of dark matter and dark energy. These mysterious components were proposed in part to explain why the cosmos looks the way it does at large scales. But in a fractal universe, their roles, or even their existence, might need rethinking. Some theorists suggest gravity alone could create fractal patterns if initial conditions were just right, while others speculate that an undiscovered physical process, something beyond Einstein's equations, might be at work. The implications ripple beyond science. A fractal cosmos would mean there's no average region of space, no true center or edge, just an infinite regression of structure. It's humbling to consider that the Milky Way might be a speck in a cluster that's itself a speck in a supercluster ad infinitum. Whether fractal cosmology holds up or not, it forces us to confront a deeper question. Are we seeing the universe clearly, or are we trapped in a perceptual hall of mirrors, mistaking one level of the pattern for the whole? The cosmic microwave background is supposed to be the ultimate cosmic equalizer, a nearly uniform glow left over from the Big Bang, showing only tiny, random temperature variations. But what if we've been wrong? What if, hidden in this ancient light, there's a pattern so unsettling that scientists call it the axis of evil, a name borrowed straight from dystopian fiction? This isn't just a minor anomaly. It's a series of alignments in the universe's oldest light that seem to point toward a mysterious preferred direction, as if the cosmos itself has a north and south pole. And if that's true, it could shatter one of our most sacred assumptions about the universe, that it's the same in every direction. The story begins with detailed maps of the cosmic microwave background, particularly those from the Wilkinson Microwave Anisotropy Probe and later the Planck satellite. These missions revealed something strange. The fluctuations in temperature weren't entirely random. Instead, they appeared to line up along a particular axis, stretching across the sky like an invisible spine. Even more bizarre, this axis eerily aligns with our solar system's plane, as if we're somehow central to the universe's architecture, a notion that clashes violently with the Copernican principle, which states we don't occupy any special place in the cosmos. At first, scientists dismissed it as an observational fluke, a trick of measurement or data processing, but the more we looked, the more the anomaly persisted. The so-called quadrupole and octupole moments, fancy terms for specific patterns in the temperature variations, weren't just misaligned, they were coordinated, whispering of a deeper structure we don't yet understand. Some researchers propose that it might be evidence of a pre-Big Bang universe, a shadow of a previous cosmic cycle imprinted on the fabric of space-time. Others suggested our universe might be bumping against another in a higher dimensional multiverse, leaving a gravitational dent in our sky. Then there's the truly radical idea that the universe isn't isotropic at all, that it has a fundamental asymmetry built into its very foundation. If true, this would rewrite textbooks overnight. Dark energy might behave differently along certain axes, gravity could vary by direction, and even the expansion of space itself might not be as uniform as we thought. The implications would ripple through every field of cosmology, forcing us to question whether the universe is truly indifferent to our place within it, or if, against all odds, we're seeing the first hints of a cosmic fingerprint, a design woven into reality itself. Of course, skeptics argue the axis of evil could still be a statistical mirage, a coincidence magnified by human pattern-seeking instincts, but the longer it lingers in our data, the harder it becomes to ignore. Future missions like next-generation space telescopes or ultra-precise polarization measurements might finally settle the debate. Until then, this eerie alignment remains one of cosmology's most tantalizing loose ends, a whisper that the universe might not just be stranger than we imagined, but stranger than we can imagine. And if it's real, it means the cosmos isn't just a vast, indifferent expanse. It might have a hidden architecture, a silent axis around which everything quietly turns. Time crystals sound like something ripped from a science fantasy novel, matter that moves in a repeating cycle without energy, forever changing yet never settling into equilibrium. But these bizarre structures aren't just theoretical whimsy, they're real, and they might be hiding in the fabric of the universe itself, Unlike ordinary crystals, where atoms arrange themselves in repeating patterns in space, time crystals repeat in time. Picture a clock that ticks perpetually without being wound, or a ring of atoms that oscillates between configurations endlessly, not because it's powered, but because it's fundamentally stuck in a loop, a groove etched into the universe's code. The idea was first proposed by Nobel laureate Frank Wilczek in 2012, and it immediately sparked controversy. Traditional thermodynamics insists that all systems eventually settle into equilibrium, like a cup of coffee cooling to room temperature. Time crystals flip this on its head, suggesting certain quantum systems can resist equilibrium entirely, locked in persistent motion without energy input. At first, even physicists doubted it was possible until experiments in 2017 created tiny time crystals in labs using chains of ions or defects in diamonds, proving these enigmatic structures weren't just mathematical curiosities. They were real. What makes time crystals so revolutionary is how they exploit quantum entanglement, that eerie connection between particles where changing one instantly affects another, no matter how far apart. In a time crystal, particles are entangled in such a way that their collective behavior repeats at fixed intervals, like a cosmic drumbeat echoing through the quantum realm. This periodicity isn't driven by external forces, but is baked into the system's quantum rules, making it a self-sustaining rhythm of matter. The implications for the universe's hidden structures are staggering. If time crystals exist naturally, perhaps forged in the extreme conditions of neutron stars or lurking in the vacuum of empty space, they could hint at temporal architectures we've never noticed. Imagine cosmic phenomena that pulse with perfect regularity across eons, not because of external influence, but because the universe itself forces them into rhythmic existence. Some theorists speculate that dark matter might consist partly of time crystal-like phases, their perpetual motion explaining why it doesn't clump like ordinary matter. Others suggest that time crystals could be relics of the early universe, freeze frames of quantum behavior from the first moments after the Big Bang. Even wilder is the possibility that time crystals might allow us to probe the nature of time itself. In Einstein's relativity, time is flexible, stretching and compressing with gravity and velocity. But time crystals introduce a new layer, structures where time's flow isn't just malleable but patterned, with physics permitting matter to mark time intrinsically, like a built-in metronome. If we could harness them, they might lead to clocks of unimaginable precision, or even clues to quantum gravity, the long-sought theory to unify relativity and quantum mechanics. Of course, mysteries remain. No one knows if naturally occurring time crystals are out there or how large they could grow, but their very existence proves that the universe still has tricks up its sleeve, structures that defy intuition, not in distant galaxies but in the quantum fabric all around us. Time crystals don't just challenge our understanding of matter, they whisper that time itself might have textures we're only beginning to sense. And if that's true, then the universe isn't just a place where things happen, it's a place where time dances. Somewhere in the depths of space, hidden behind the thick dust and stars of our own Milky Way, there's a force so powerful it's pulling entire galaxies toward it at millions of miles per hour. This is the Great Attractor, a gravitational mystery so colossal it warps the motion of everything around it, yet remains almost invisible to our telescopes. Picture a cosmic whirlpool, its current dragging thousands of galaxies, including our own, toward an unseen center. The strangest part, we don't fully know what's causing it. The discovery began decades ago when astronomers noticed something odd about the Milky Way's motion. Even after accounting for the expansion of the universe and the pull of nearby galaxy clusters, our galaxy, along with countless others, was being tugged toward a specific point in space, roughly 250 million light-years away in the direction of the constellation Centaurus. The force behind this movement had to be unimaginably massive, equivalent to tens of thousands of Milky Ways crammed into one region. but when scientists pointed their telescopes there, they found almost nothing. The problem is something astronomers call the zone of avoidance, a swath of sky obscured by the dense gas, dust, and stars of our galaxy's disk. It's like trying to peer through a fogged-up window. The Great Attractor lies directly behind this cosmic blind spot. Early X-ray and infrared surveys hinted at a monstrous concentration of mass, likely a supercluster of galaxies dubbed the Norma Cluster, but its gravity alone couldn't explain the staggering pull. The numbers didn't add up. Whatever was lurking there had to be far more immense, far stranger. Recent observations have peeled back some of the mystery. By mapping galaxies' motions in 3 dimensions, astronomers uncovered an even larger structure behind the Great Attractor, the Laniakea supercluster, a web of galaxies spanning 500 million light-years with the Great Attractor near its heart. Think of it as a gravitational valley where galaxies flow like rivers toward the deepest point. Yet even Laniakea might not be the full story. Some theories suggest the Great Attractor could be a portal to something beyond, a knot in space-time where dark matter filaments converge, or a bridge to another, denser supercluster we've yet to map. The implications are dizzying. If the Great Attractor is stronger than visible matter can explain, it might be the fingerprint of dark matter woven into structures we're only beginning to perceive. Or it could signal flaws in our understanding of gravity itself, a cosmic clue that Einstein's equations need revising on the largest scales. Every new observation, from radio telescopes piercing the zone of avoidance to gravitational wave detectors sensing unseen mass, brings us closer to answers. But the Great Attractor remains one of the universe's most tantalizing enigmas. So while we can't yet see it clearly, we can feel its pull. Every second, the Milky Way races toward this hidden leviathan at over 1 million miles per hour, caught in a current older than the dinosaurs. One day, billions of years from now, we might reach it. Until then, it stands as a reminder. The universe is full of invisible giants, and we're just beginning to learn their names. Among the towering filaments and glittering galaxy clusters of the cosmic web, there exist regions so empty they defy intuition, cosmic voids, unimaginably vast deserts of near-nothingness spanning hundreds of millions of light-years. These aren't just gaps between galaxies, they're staggering abysses where matter is almost entirely absent, as if the universe forgot to fill in the blanks. The Boötes Void, one of the largest known, stretches 330 million light-years across and contains only a handful of galaxies, a cosmic ghost town where you could travel for eons without encountering a single star. What makes these voids so perplexing isn't just their emptiness, but how they shape the universe around them. While galaxies flock to dense filaments and clusters, the voids exert their own subtle influence, acting like repulsive zones where space itself expands faster than average. Picture squeezing a sponge. The denser regions are the wet clumps, but the voids are the pockets of air that stretch and distort the entire structure. This accelerated expansion within voids isn't driven by dark energy alone, though it amplifies the effect, but by the sheer lack of gravity from missing matter. With so little mass to pull space back, these regions become cosmic speed zones, stretching the fabric of reality faster than their surroundings. Theories about their origins trace back to the universe's infancy. In the primordial soup of the Big Bang, tiny quantum fluctuations seeded variations in density. Slightly denser patches grew into galaxies, while the emptier regions ballooned into voids. But the mystery lies in how they grew so large. Some models suggest mergers between smaller voids, like bubbles combining in a boiling pot, while others propose that dark energy's repulsive force actively sculpted them, pushing matter aside like an invisible hand. There's even a radical idea that voids could contain exotic forms of dark energy, their emptiness hiding a different kind of physics altogether. Yet voids aren't entirely barren. Scattered galaxies occasionally cling to life within them, often strange, isolated systems evolving in profound solitude. These void galaxies are like castaways on deserted islands, their star formation stunted by the lack of cosmic neighbors. Studying them offers clues about how environment shapes galaxies and hints that voids might be more dynamic than we thought. Some simulations show galaxies being flung into voids along dark matter currents, like driftwood caught in a tide, only to be pulled back out eons later. The most mind-bending implication, voids might be the ultimate architects of the cosmic web. Their expansion presses surrounding matter into dense sheets and filaments, like dough squeezed between fingers. Without voids, the universe might lack the intricate structure we see today. No glittering galaxy clusters, no sprawling superclusters, just a monotonous fog of stars. They're the negative space that gives the cosmos its shape, the silent backdrop against which all else unfolds. So while they seem like cosmic afterthoughts, voids hold profound secrets. They challenge our understanding of gravity, dark energy, and the very nature of emptiness. If the universe is a grand puzzle, voids aren't just the missing pieces, they're the empty spaces that make the picture whole. And as we map their echoing depths, we might just find that nothingness in its own way holds the key to everything. What if black holes aren't cosmic dead ends but gateways to entire universes, and our own universe is nestled inside one? This is the black hole universe hypothesis, a theory so audacious it reimagines the Big Bang as the birth throes of a singularity in some higher dimensional reality. Picture a matryoshka doll of existence, where every black hole in our universe contains another cosmos, and our own universe is just one layer in an infinite stack. It sounds like science fiction, but the math behind it is startlingly elegant, weaving together relativity, quantum mechanics, and cosmology into a radical new vision of reality. The idea stems from a simple but profound observation. The equations describing the collapse of matter into a black hole bear an uncanny resemblance to those describing the expansion of the universe in reverse. When a star collapses, its matter crushes into an infinitely dense point, a singularity. But flip the process backward and you get something that looks eerily like the Big Bang, an explosion of energy and space from a single point. This symmetry led physicists like Nikodem Poplawski to propose that what we call the Big Bang might have been the formation of a black hole in a parent universe, with our entire cosmos unfolding inside its event horizon. Here's where it gets even stranger. General relativity suggests that time slows to a crawl near a black hole's event horizon, stopping entirely from an outsider's perspective. But for someone falling in, time would appear normal, meaning that while the parent universe might see our universe as frozen in the birth moment, for us, billions of years could pass in what seems like an instant. This time warping effect could explain why our universe appears so finely tuned for life. The constants of physics might simply be inherited from the conditions of the parent black hole's formation, like genetic traits passed between cosmic generations. The implications ripple through every corner of physics. If our universe is inside a black hole, the event horizon isn't a distant boundary. It's the edge of our observable cosmos, the cosmic microwave background. The uniformity of that ancient light could be the stretched remnants of quantum fluctuations from the parent black hole's formation, imprinted on our universe like a birthmark. Even dark matter might find an explanation. It could be debris from the parent universe drifting through the walls of our cosmic cell. Critics argue the theory is untestable. How could we ever peer beyond our universe's event horizon? But supporters point to subtle clues. If black holes birth universes, their spin and charge should imprint on the physics of the offspring cosmos, potentially leaving detectable patterns in large-scale structure or the cosmic microwave background. Some even speculate that quantum entanglement, the eerie link between particles across vast distances, could be a remnant of connections to the parent universe, like umbilical cords threading through the singularity. Whether the black hole universe hypothesis holds or not, it forces us to confront a humbling possibility. that the vast expanse we call home might be just one infinitesimal layer in an infinite cosmic onion, each universe hidden inside the very objects we thought were its end. It's a reminder that the universe's greatest mysteries might not lie in the distant galaxies but in the dark hearts of black holes, waiting to be unraveled. Right now, dark energy is pushing the universe apart at an ever-increasing rate, but what if it's just getting started? The phantom energy hypothesis takes this already unsettling idea and cranks it up to terrifying extremes. Imagine a force that doesn't just accelerate cosmic expansion but grows stronger over time, like a snowball rolling downhill, gathering mass and momentum until it becomes an avalanche capable of tearing apart the very fabric of reality. This isn't just a hypothetical doomsday scenario, it's a real possibility lurking in the equations of cosmology, and if it's true, the universe's fate isn't just cold and dark, it's violent, chaotic, and utterly apocalyptic. The key lies in the nature of dark energy itself. Most models treat it as a constant, an unchanging energy density woven into empty space. But phantom energy flips the script, proposing that dark energy's density could actually increase as the universe expands. Picture blowing up a balloon, but instead of the rubber stretching thinner, it somehow grows thicker and more rigid the larger it gets. The consequences are catastrophic. If dark energy strengthens indefinitely, it wouldn't just push galaxies apart, it would overwhelm every force holding matter together, from galaxy clusters down to atoms themselves. First, galaxy clusters would be ripped apart as the space between them stretches faster than light can cross it. Then, individual galaxies would unravel, stars torn from their orbits and flung into the void. Eventually, even solar systems, planets, and finally atoms would be shredded as the phantom tide grows strong enough to snap the bonds of gravity, electromagnetism, even the nuclear forces that glue quarks together. The end point, the Big Rip, a singularity of disintegration where space itself is stretched so violently that time loses all meaning. Unlike the heat death of the universe, where everything fades into a cold, quiet equilibrium, the Big Rip is a crescendo of destruction, a final moment where the universe's expansion rate becomes infinite. It's the difference between a candle flickering out and a bomb exploding. What makes this idea so chilling is how little we'd see it coming. Current observations can't definitively rule out phantom energy, and some measurements of dark energy's equation of state, the ratio of its pressure to its density, hint at values slightly more negative than -1, the threshold where phantom behavior begins. If confirmed, it would mean the countdown is already ticking, with estimates placing the Big Rip anywhere from tens of billions to just a few 100 million years from now. Yet the most fascinating part isn't just the destruction, it's what phantom energy tells us about the universe's hidden rules. If dark energy can evolve, it might be tied to an undiscovered field or particle, something even more exotic than current theories suggest. Some models propose it could be linked to vacuum decay, where the universe's underlying quantum fields tunnel into a lower energy state, rewriting the laws of physics in an instant. Others speculate that phantom energy could be a sign of extra dimensions leaking influence into our reality, or evidence that Einstein's cosmological constant isn't constant at all. For now, the phantom energy hypothesis remains on the fringe, but it's a stark reminder of how fragile cosmic structure really is. The same force driving the universe's expansion, the engine behind galaxies racing apart and the cosmic web stretching thin, could one day turn against everything it helped create. And if that day comes, the universe won't just fade away. It'll scream into the void, torn apart by its own accelerating heartbeat. Picture this: you suddenly wake up floating in complete darkness. No body, no memories, just a solitary consciousness blinking into existence, a lone brain that formed randomly from the chaotic churn of particles in the void. This isn't a nightmare, it's the Boltzmann-Brane paradox, one of the most unsettling ideas in physics. Named after the 19th century physicist Ludwig Boltzmann, This thought experiment flips our understanding of reality on its head by suggesting that in an infinite, chaotic universe, self-aware entities could spontaneously arise from sheer randomness. The logic starts with entropy, the universe's tendency toward disorder. Boltzmann realized that given enough time, even the most improbable events become inevitable. In a cosmos that's existed for trillions of years, particles bouncing around at random could, by sheer chance, arrange themselves into a functioning brain complete with fabricated memories of a past that never happened. Statistically, it's far more likely for a single, isolated brain to pop into existence than for an entire orderly universe like ours to emerge from chaos. So if you accept the laws of probability, the unnerving question follows: how do you know you're not one of those random, temporary aberrations? This paradox isn't just a philosophical curiosity, it's a genuine problem for cosmology. If the universe is eternal or cyclic, as some theories suggest, then Boltzmann brains should vastly outnumber real observers like us. Yet here we are, seemingly embedded in a coherent, stable reality with consistent laws of physics. One way out is to argue that our universe isn't eternal but had a definite beginning, like the Big Bang, which reset the entropy clock and made structured reality more probable than randomness. Another possibility is that the universe is fundamentally holographic or computational, with underlying rules that prevent such aberrations from forming. But the implications run deeper. If consciousness can arise from random fluctuations, what does that say about the nature of our own minds? Are we just temporary patterns in the cosmic noise, destined to dissolve as quickly as we formed? Some physicists dismiss Boltzmann brains as absurd after all. If they were common, we'd expect to wake up mid-void, not in a richly detailed world. Others see the paradox as a clue that our understanding of time, entropy, or quantum mechanics is incomplete. The Boltzmann brain forces us to confront the fragility of existence. It's a reminder that in a universe governed by probability, even the most fundamental truths like the reliability of memory or the solidity of reality might hang by a thread. Whether a clever riddle or a genuine cosmic warning, this paradox leaves us with one chilling thought. In the grand casino of existence, we might not be the house. We might just be a fleeting roll of the dice. What if the key to understanding dark matter and much of the universe's hidden architecture has been hiding in plain sight since the dawn of time? Enter primordial black holes, hypothetical relics from the universe's first chaotic moments. These aren't the colossal black holes formed from dying stars. They're microscopic, some no heavier than an asteroid yet denser than a mountain, forged in the searing pressures of the Big Bang itself. If they exist, they could be the invisible scaffolding of the cosmos, lurking unseen while shaping everything from galaxies to the very fabric of space. The theory hinges on a radical idea that in the first fraction of a second after the Big Bang, tiny fluctuations in density could have collapsed into black holes. Picture the infant universe as a frothing, violent sea, where pockets of space-time pinch off into gravitational knots so tight even light can't escape. Unlike stellar black holes, which take eons to form, these primordial ones would have appeared instantaneously, peppering the cosmos like cosmic shrapnel. Some might have evaporated almost immediately, thanks to Hawking radiation, while others, those with enough mass, could have survived for billions of years, drifting through the universe like invisible ghosts. Here's where it gets revolutionary. These ancient black holes could solve one of cosmology's biggest headaches: dark matter. We know dark matter exists because galaxies rotate too fast for the gravity of visible matter to hold them together, and galaxy clusters bend light more than they should. But all our attempts to detect dark matter particles have come up empty. Primordial black holes offer an elegant alternative. If enough of them formed in the early universe, their collective gravity could precisely account for dark matter's gravitational effects, no exotic particles required. They'd be the universe's ultimate dark currency, invisible yet indispensable. But how would these tiny black holes influence the cosmos today? Simulations suggest they'd cluster in the halos around galaxies, their gravity subtly sculpting the distribution of stars and gas. Some might occasionally pass near stars, their gravitational tug creating faint but detectable anomalies in starlight. Others could collide, sending ripples through space-time that our gravitational wave detectors might someday catch. And if they're dense enough, they could even act as cosmic lenses, bending distant light in ways that reveal their presence. The hunt for primordial black holes is already underway. Astronomers scour microlensing surveys for telltale flashes caused by these objects drifting in front of stars. Others analyze the cosmic microwave background for hints of their early influence. Even gravitational wave observatories listen for the unique chirps of tiny black holes merging. So far, no smoking gun, but the search has narrowed their possible mass range, ruling out some versions of the theory while leaving others tantalizingly plausible. Critics argue that primordial black holes would have left more obvious scars, like disrupting neutron stars or distorting the universe's oldest light. But supporters counter that their interactions could be rarer or subtler than we think, their signatures hiding in plain sight. Whether they're the missing piece of the dark matter puzzle or just another cosmic dead end, primordial black holes force us to confront a humbling possibility: that the universe's darkest secrets might not lie in undiscovered particles, but in forgotten relics from its very first breath. And if we find them, it wouldn't just rewrite the story of dark matter, it would reveal a cosmos far stranger and far more inventive than we ever imagined. In the intricate puzzle of the cosmos, few missing pieces are as perplexing or as promising as magnetic monopoles. These hypothetical particles, first proposed by physicist Paul Dirac in 1931, carry just a single magnetic pole, either a north or a south, never both. To grasp how strange this is, imagine cutting a bar magnet in half. Instead of isolating the poles, you'd always end up with two smaller magnets, each still sporting both ends. Monopoles defy this expectation, behaving like electric charges, but for magnetism, a fundamental asymmetry that, if real, could rewrite our understanding of the universe's deepest symmetries. The hunt for monopoles isn't just academic curiosity, it's a quest to solve one of physics' grandest riddles. Dirac showed that their existence would perfectly explain why electric charge comes in discrete, quantized units, like the ticks of a cosmic ruler. Even more compelling, monopoles emerge naturally from grand unified theories models that attempt to stitch together the electromagnetic, weak, and strong nuclear forces into a single framework. These theories suggest that in the searing heat of the early universe, symmetry-breaking phase transitions could have forged monopoles as topological defects, like cracks forming in ice as it freezes. If true, they'd be fossils from a time when the forces we know today were indistinguishable, offering a direct window into the universe's first trillionth of a second. Yet despite decades of searching, from deep underground labs to cosmic ray detectors, monopoles remain elusive. Some experiments have turned up tantalizing false alarms, like the infamous 1982 event in a Stanford lab where a solitary signal matched a monopole's predicted signature only to never repeat. Others have scoured ancient minerals and meteorites, hunting for scars left by monopoles traversing solid rock over eons. Even the Large Hadron Collider has joined the search, smashing particles at unprecedented energies in hopes of manufacturing these exotic relics. The implications of finding them would ripple across physics. Monopoles could validate grand unification, hinting at a cosmos where all forces were once one. They might even hold clues to dark matter, with some theories suggesting stable monopoles could form invisible, massive structures that shape galaxies. And if they interact with magnetic fields as predicted, they'd create distinctive trails in space, cosmic breadcrumbs we might one day follow to their source. For now, the monopole remains a ghost in the equations, a whisper of a more symmetrical universe hiding just beyond our reach. But the search continues, driven by the thrilling possibility that somewhere in a lab, a meteorite, or the depths of space, a single magnetic north or south might be waiting to rewrite the rules of reality. And if we find it, we won't just uncover a new particle, we'll glimpse the universe's hidden blueprints etched in the language of magnetism itself. Every second, trillions of nearly invisible particles streak through your body at the speed of light, leaving no trace. These are neutrinos, ghosts of the subatomic world, so elusive they can pass through light years of lead without a single interaction. Yet despite their faint whispers in the cosmos, neutrinos might hold the keys to some of the universe's largest structures, sculpting galaxies and galaxy clusters in ways we're only beginning to understand. Born in the hearts of stars, supernova, and even the Big Bang itself, neutrinos outnumber atoms in the universe by 1,000,000,000 to 1. For decades, physicists assumed they were massless, zipping through space without a care, until experiments in the late 1990s revealed a shocking twist: neutrinos have mass. Not much. A single neutrino is at least 500,000 times lighter than an electron, but in a cosmos teeming with them, that tiny weight adds up. Collectively, they could rival all the visible stars in the universe, forming a vast, invisible sea that ebbs and flows through the cosmic web. Here's where things get fascinating. Neutrinos move at nearly the speed of light, making them the universe's ultimate cosmic speedsters. But unlike dark matter, which clumps together under gravity, neutrinos resist staying in one place. Their blistering velocity gives them a kind of gravitational slipperiness, smoothing out the densest regions of the early universe like a cosmic iron. This subtle tug of war between their gravity pulling matter together and their momentum pushing it apart could explain why galaxy clusters formed where they did, and why some regions of space remain eerily empty. Yet for all their influence, neutrinos are maddeningly hard to pin down. Detecting them requires monstrous experiments like Japan's Super Kamiokande, a tank filled with 50,000 tons of ultra-pure water buried deep underground, waiting for the rare flash of light when a neutrino collides with an atom. Even then, we've only scratched the surface of their mysteries. Neutrinos come in 3 known flavors: electron, muon, and tau. And they can morph between these types mid-flight, a quantum chameleon act that still baffles physicists. Some theories even suggest there could be a 4th, sterile neutrino, interacting with nothing except gravity, hiding in plain sight. What's at stake isn't just academic. If sterile neutrinos exist, they could be the missing link between the neutrino world and dark matter, 2 of cosmology's greatest puzzles. Their unique properties might also explain why the universe is made of matter instead of antimatter, a bias that allowed stars, planets, and us to exist at all. And because neutrinos carry unfiltered signals from the universe's most violent events, like supernova and colliding black holes, decoding their secrets could open a new window into the cosmos's hidden workings. So the next time you look up at the night sky, remember, it's not just stars and galaxies you're seeing. It's a universe threaded with invisible, near-weightless phantoms, quietly shaping everything from the largest structures to the fate of matter itself. And somewhere in their ghostly dance, the answers to our biggest questions might already be flowing right through our hands unseen. What if the entire universe operates like a living organism, constantly adjusting and balancing itself to maintain stability? This is the cosmic scale Gaia hypothesis, an idea that stretches Earth's delicate self-regulation to the grandest possible canvas, the cosmos itself. On our planet, the Gaia theory suggests that life doesn't just adapt to its environment, but actively shapes it, with organisms influencing everything from atmospheric composition to ocean chemistry in a vast, interconnected dance. Now imagine that same principle applied to galaxies, dark matter, and the very fabric of space-time. Could the universe, too, have mechanisms that unconsciously steer it toward equilibrium, like a cosmic immune system? At first glance, the idea seems lifted from science fiction, until you notice the eerie fine-tuning of the cosmos. The constants of nature, like the strength of gravity or the mass of an electron, are so precisely calibrated that even slight deviations would render stars, planets, and life itself impossible. Coincidence? The cosmic Gaia hypothesis proposes a different explanation, that the universe might possess feedback loops, subtle mechanisms that correct imbalances over vast timescales. Picture dark energy adjusting its push to counteract gravitational collapse, or black holes acting as regulators, consuming excess matter to prevent runaway star formation. Even the cosmic web's intricate filaments could function like a neural network, transmitting information or influence across unimaginable distances. One provocative version of this theory suggests that life and consciousness aren't accidental byproducts of the universe but integral components of its self-regulation. Just as trees on Earth stabilize climates by absorbing carbon, advanced civilizations might unknowingly contribute to cosmic equilibrium, perhaps by harnessing energy in ways that mitigate entropy or stabilize galactic structures. It's a dizzying thought that intelligence scattered across the stars could be part of the universe's subconscious toolkit for preserving itself. Critics argue this veers into metaphysics, lacking the rigorous math of conventional cosmology. But supporters point to emerging clues: the universe's large-scale structure, its filaments, voids, and clusters, mysteriously avoids extremes as if bound by invisible guardrails. Even the distribution of dark matter appears oddly balanced, neither too clumpy nor too smooth. Could these be signatures of a deeper, self-correcting order? Some models of quantum gravity hint that space-time itself might possess a form of memory or adaptability, evolving in response to its own state like a living tissue healing a wound. Whether poetic speculation or profound truth, the cosmic Gaia hypothesis challenges our place in the universe. We're not just passive observers of a mechanical cosmos, but potential participants in something far more dynamic, a universe that doesn't just exist but evolves, reacts, and perhaps even sustains itself. And if that's true, then every star, every atom, and every conscious thought might be part of a grand, self-aware dance we're only beginning to perceive. What if every choice you've ever made, every triumph, every heartbreak has already happened an infinite number of times and will happen again forever? This is the chilling premise of the time loop universe theory, a cosmic vision where existence isn't just cyclical in structure, but in every moment, every event locked in an endless replay. Unlike the Big Bounce, where the universe collapses and rebirths with new variations, this model suggests time itself is a closed loop, an Ouroboros eating its own tail, with history destined to repeat identically down to the smallest quark. The roots of this idea stretch back to Einstein's general relativity, where solutions to the equations allow for closed time like curves, paths through space-time that return to their starting point. Picture a record spinning on a turntable. The needle moves forward, yet the groove circles back endlessly. In a time loop universe, the arrow of time might bend into a circle, with the Big Bang not just birthing the cosmos but also serving as its inevitable end, collapsing back into the singularity only to explode outward again in the same sequence. The stars would ignite with identical light, civilizations would rise and fall with the same words and wars, and you'd be sitting here right now watching this video again and again and again. The implications for free will are staggering. If the universe is locked in an unbreakable cycle, are our choices truly our own, or just scripted beats in a cosmic rerun? Philosophers have wrestled with this for centuries, but the time loop model cranks the paradox to extremes. Even the sensation of making a decision could be an illusion, a pre-recorded moment playing out on a universe-sized tape. Some interpretations suggest consciousness itself might be the only thing that feels new each cycle, like a dreamer trapped in a recurring nightmare, unaware they've lived it before. Yet there's a haunting beauty to this idea. In a time loop cosmos, nothing is ever truly lost. Every smile, every discovery, every act of love is etched eternally into the fabric of reality, replaying like a favorite song. It's a universe without final goodbyes, where every ending is a beginning in disguise. Even entropy, the inevitable decay of order, might reset with each cycle, erasing its own scars as the loop resets. Could we ever prove such a loop exists? Some physicists propose that if the universe eventually recollapses, subtle quantum effects might carry echoes of prior cycles forward, imprinting faint patterns in the cosmic microwave background or gravitational waves. Others speculate that advanced civilizations might leave time capsules, artifacts, or encoded messages designed to survive the reset, like a note passed to one's past self. But the most profound question remains: if time is a loop, why does it feel linear? Why do we remember the past but not the future? Here, the theory brushes against the hard problem of consciousness, suggesting that perception of time's flow might be a side effect of how our brains process information within the loop, like a movie feeling sequential even though all its frames exist simultaneously. Whether poetic metaphor or physical reality, the time loop universe forces us to confront the fragility of meaning. In a cosmos where everything repeats, do our lives hold weight, or are we just shadows on a cave wall, dancing to laws we can't escape? The answer might lie beyond physics, in the spaces between mathematics and metaphysics, where time, for all its power, is just another thread in the universe's tapestry, woven into a circle with no end and no beginning. If black holes are the universe's ultimate one-way streets, swallowing everything that crosses their event horizon, then white holes are their theoretical opposites, cosmic fire exits, violently spewing out matter and energy with no way back in. Imagine a black hole in reverse. Instead of an inescapable gravitational pit, a white hole would be an impenetrable mountain, ejecting material at such ferocious speeds that nothing could ever climb inside. While black holes have been observed and studied for decades, white holes remain purely hypothetical, lurking in the equations of general relativity as tantalizing possibilities that could rewrite our understanding of cosmic architecture. The math behind white holes is eerily symmetrical. Einstein's field equations don't care about the direction of time, meaning that if black holes exist, there's no fundamental reason their time-reversed counterparts couldn't too. Picture a film of a black hole collapsing in reverse. Instead of matter falling inward, it's expelled outward in a dazzling burst. But here's the catch: white holes violate the second law of thermodynamics, which states that entropy, or disorder, always increases. A white hole would essentially be a cosmic reset button, spraying out pristine, organized energy into the universe, seemingly defying nature's preference for chaos. This paradox makes many physicists skeptical, yet the idea persists because of its dazzling implications. One radical theory suggests that white holes could be the other end of black holes, connected by wormholes through space-time. In this model, a black hole's singularity might not be a dead end but a tunnel, with matter and energy reappearing elsewhere in the cosmos, or even in another universe via a white hole's eruption. It's a cosmic version of threading a needle through folded fabric. Plunge into a black hole here, and you might emerge from a white hole light years away. Some interpretations even propose that the Big Bang itself was a white hole event, the ultimate cosmic outburst birthing our universe from the collapse of another. Then there's the quantum angle. Recent work in loop quantum gravity suggests that when a black hole's evaporation via Hawking radiation nears completion, quantum effects might rebound its collapse into a white hole explosion. Instead of vanishing into nothingness, a black hole could transform, shattering into a fountain of particles and energy as it reaches microscopic scales. These quantum white holes wouldn't last long, just fractions of a second, but their fleeting existence could solve the black hole information paradox, ensuring no data is ever truly lost to the void. The challenge, of course, is evidence. White holes would be spectacularly bright, but we've never observed an astrophysical object matching their description. Some theorists argue that gamma-ray bursts, the most energetic event since the Big Bang, could be white holes blinking into existence, while others speculate that dark matter's gravitational effects might hint at their presence. For now, they remain ghosts in the equations, cosmic mirages that tantalize with their elegance but refuse to materialize. Yet the white hole hypothesis does more than tease our imagination. It forces us to confront the universe's hidden symmetries. If black holes exist, why not their inverses? If time can bend, why can't it fold back on itself? Whether or not white holes are real, their possibility reminds us that the cosmos is far stranger than the rules we've scribbled in our textbooks. And somewhere in the darkness between the stars, there might just be a door waiting to burst open. Deep inside neutron stars, the universe's densest objects outside black holes, matter undergoes transformations so extreme they defy the laws of physics as we know them. Here, pressures are 100 trillion times greater than Earth's, temperatures reach 1,000,000 degrees, and atoms are crushed into a sea of neutrons so tightly packed they behave like a single, gargantuan atomic nucleus. But what if, beneath this chaotic surface, neutron stars conceal something even stranger? Vast crystalline cores where matter arranges itself into orderly, lattice-like structures akin to diamonds forged in the heart of a cosmic furnace. The idea hinges on a phenomenon called nuclear posture, a bizarre phase of matter unique to neutron stars. As gravity overwhelms atomic forces, protons and electrons fuse into neutrons, but they don't stop there. Under increasing pressure, these neutrons arrange into ever weirder shapes, first gnocchi, sphere-like clusters, then spaghetti, elongated strands, and finally lasagna, flat sheets. These formations aren't just whimsical nicknames, they're real configurations predicted by quantum simulations, where the rules of symmetry and stability bend under unimaginable strain. If conditions push further, these posture phases might crystallize into a solid, ultra-dense lattice, a neutron star's core frozen into a rigid, metallic-like state. What would this crystal core look like? Picture a grid where each point isn't an atom but a cluster of neutrons, packed so tightly they vibrate against one another like springs in a cosmic mattress. The energy required to disrupt this structure would be staggering, making it harder than diamond by orders of magnitude. Some theories even suggest these crystals could vibrate at specific frequencies, ringing like colossal tuning forks and emitting gravitational waves detectable across the galaxy. Others propose that defects in the crystal-tiny misalignments in the lattice might store exotic forms of energy or even create stable pockets where strange new particles could form. The implications ripple far beyond neutron stars. If such crystals exist, they'd be a Rosetta Stone for understanding matter under conditions impossible to replicate on Earth. Laboratories like CERN can smash particles at near light speeds, but they can't sustain the crushing, sustained pressures found in neutron star cores. These cosmic crystals would offer a natural lab for testing quantum chromodynamics, the theory governing how quarks and gluons interact. They might even unveil clues about superfluidity, the frictionless flow of matter, or superconductivity at energies that dwarf anything achievable in human experiments. Yet the wildest possibility is that these crystals aren't just inert structures. Some models suggest they could remember shifts in the neutron star's rotation, storing angular momentum like a cosmic flywheel. If the star's spin suddenly changes, say, during a starquake or magnetic upheaval, the crystal core might fracture and reform, releasing energy in bursts of X-rays or gravitational waves. This could explain mysterious phenomena like gamma-ray flares or glitches in pulsar timing, where neutron stars seemingly speed up without warning. Of course, proving any of this is a monumental challenge. Neutron stars are notoriously opaque. Their interiors are shielded by impenetrable plasma and gravity so strong it bends light into a death spiral, but astronomers aren't completely blind. Gravitational wave observatories like LIGO and Virgo could one day catch the resonant hum of a crystalline core vibrating after a collision. X-ray telescopes might detect patterns in neutron star spectra hinting at rigid surface layers. Even quantum simulations run on next-generation supercomputers could reveal whether these crystals are stable or just fleeting fantasies of mathematical models. Whether neutron stars truly harbor these diamond-like hearts remains an open question, but the very possibility stretches our imagination, revealing how little we understand about matter pushed to its breaking point. If these cosmic crystals are real, they're more than just scientific curiosities, they're monuments to the universe's capacity for invention, forging order in the most chaotic crucibles imaginable. And locked within their perfect lattices might be secrets that rewrite physics itself. Quantum gravity is the ultimate puzzle in physics, two sets of rules that refuse to merge no matter how hard we try. On one hand, quantum mechanics flawlessly describes the subatomic world, where particles pop in and out of existence and reality blurs into probabilities. On the other, Einstein's general relativity paints space-time as a smooth, bending fabric warped by stars and black holes. Yet when these theories collide, the math explodes into nonsense, screaming that somewhere we've missed a cosmic memo. Solving this rift isn't just academic, it could unveil hidden layers of reality, structures so subtle they've eluded us simply because we lack the right lens to see them. Enter string theory, one of the boldest attempts to bridge the divide. Imagine if every particle in the universe wasn't a point but a tiny, vibrating string, its frequency determining whether it becomes an electron, a quark, or a photon. These strings don't dance in the 3 dimensions we know. They wriggle through 10 or more, curled so tightly they're invisible to us, like ants navigating the grooves of a vinyl record. The promise: gravity emerges naturally from these vibrations, with the graviton, the hypothetical particle carrying gravitational force, just one note in the string's symphony. But the cost is a universe far more complex than we ever imagined, where every particle is a harmonic echo of deeper geometry. String theory isn't alone in this quest. Loop quantum gravity takes a radically different approach, proposing that space itself isn't smooth but woven from indivisible, thread-like loops. Picture the cosmos as a vast network, like a cosmic knit sweater, with each loop carrying a tiny quantum of area or volume. When these loops intersect, they create the fabric of space-time, and gravity arises from their interactions. Unlike strings, loops don't demand extra dimensions, but they do suggest space is granular at the smallest scales. A pixelated reality where not just matter but space and time come in discrete chunks. The implications of these theories ripple far beyond equations. If space is woven from loops, then black holes might not have singularities at their cores, but instead transition into regions where space-time unravels and reconnects in new configurations. Similarly, string theory's extra dimensions could mean our universe floats alongside others in a higher dimensional bulk, with gravity leaking between them like perfume through a curtain. Some models even suggest that cosmic inflation, the universe's explosive early growth, was triggered by 2 of these higher dimensional branes colliding, stitching our reality into existence. Yet for all their elegance, these ideas face daunting challenges. String theory's extra dimensions are so small they're effectively hidden, leaving few ways to test their existence. Loop quantum gravity, while more minimalist, struggles to explain how the fuzzy quantum nature of space smooths out into the continuous universe we observe. Both theories lie largely in the realm of mathematics, awaiting experiments bold enough to confirm or crush them. That hasn't stopped physicists from dreaming. Future gravitational wave detectors might catch whispers of extra dimensions in the echoes of colliding black holes, or particle colliders could unveil hints of supersymmetry, a key prediction of string theory where every known particle has a heavier twin. What's truly exhilarating is how these frameworks reframe cosmic architecture. If quantum gravity is real, then the universe isn't just expanding, it's vibrating, evolving, maybe even computing with every particle and force a thread in a deeper code we're only beginning to decipher. Whether through strings, loops, or some yet undiscovered structure, the search for quantum gravity isn't just about unifying physics. It's about uncovering the hidden blueprints of existence, written in a language we're still learning to read. The universe is expanding, but not everything is moving apart. In fact, entire galaxy clusters are racing in the same direction at baffling speeds, as if dragged by some unseen force beyond the edges of observable space. This isn't just random drift, it's a coordinated, large-scale motion cosmologists call dark flow, a mystery so profound it hints at influences from realms we can't even see. Dark flow first made headlines in 2008 when astronomers studying the cosmic microwave background, the afterglow of the Big Bang, noticed something bizarre. Hundreds of galaxy clusters weren't just drifting with the universe's expansion. They were streaming toward a single patch of sky at speeds exceeding 2 million miles per hour. The kicker, there was nothing visible in that direction massive enough to explain the pull. No supercluster, no dense knot of dark matter, just empty space. Yet the clusters moved as if yanked by a gravitational hand reaching from beyond the known cosmos. One explanation is as unsettling as it is thrilling. Our universe might be tugged by something outside it. Picture a fish in a pond, unaware that the current dragging it sideways comes from a waterfall just beyond the bend. Similarly, dark flow could be evidence of neighboring universes or colossal structures lurking past our cosmological horizon, their gravity warping our cosmic neighborhood. Some theories suggest these could be remnants of pre-Big Bang physics quantum fluctuations stretched to cosmic scales during inflation, imprinting a directional bias on the newborn universe. Others propose that we're brushing against a higher dimensional bulk, where gravity leaks between realities like water seeping through cracks, but not everyone's convinced. Skeptics argue dark flow could be a measurement fluke, an artifact of incomplete data or systemic errors in how we track galaxy motions. After all, mapping velocities across billions of light years is like trying to measure a breeze from another continent. Yet the signal persists in newer surveys, defying simple dismissal. If real, it challenges a cornerstone of cosmology, the cosmological principle, which states that the universe should look roughly the same in all directions on large scales. Dark flow screams otherwise, that on some level the cosmos has a preferred direction, a cosmic north pulling everything off kilter. What's at stake isn't just academic. If dark flow is real, it could rewrite our understanding of what lies beyond the observable universe. Normally, we assume nothing outside our cosmic horizon. The 46 billion light-year limit of what we can see affects us, since light from there hasn't had time to reach us. But gravity might not play by those rules. If massive enough, structures beyond that boundary could still tug on us, warping space-time like a hidden magnet bending iron filings. This would mean the universe isn't just bigger than we thought. It's weirder, with architecture stretching into unknowable depths. The hunt for answers is heating up. Upcoming telescopes like the European Space Agency's Euclid mission will map galaxy motions with unprecedented precision, searching for dark flow's fingerprints in the cosmic web. Others are probing the microwave background for subtle distortions that might betray the pull of external giants. If confirmed, dark flow wouldn't just solve a mystery, it would crack open a door to the unimaginable, revealing that our universe is just one thread in a tapestry vaster than we've dared to dream. So the next time you gaze at the night sky, remember, galaxies aren't just drifting apart. Somewhere, something immense is calling them, an invisible tide flowing from the dark beyond. And we're only just beginning to trace its current. What if the universe isn't just evolving toward chaos, but is secretly building toward an ultimate masterpiece, a point where consciousness becomes the fabric of reality itself. This is the audacious claim of Omega Point theory, a vision of cosmic destiny so grand it blurs the line between science, philosophy, and theology. Proposed by physicist Frank Tipler in the 1980s, this theory suggests that the universe isn't just a mindless machine ticking toward heat death, but a kind of cosmic incubator, nurturing intelligence until it saturates every corner of existence. Picture a future so distant it makes the age of the universe seem like a blink, a moment when all matter, energy, and even the hidden structures of space-time become infused with a singular, omnipresent awareness. The path to this Omega Point hinges on the universe's expansion. Unlike phantom energy's apocalyptic Big Rip, Tipler's model predicts a Big Crunch, where dark energy weakens and gravity eventually pulls everything back together in a fiery collapse. But here's the twist: as the universe contracts, the energy density skyrockets, creating conditions for infinite computational power. Intelligent civilizations, humanity's distant descendants or alien minds, would harness this energy to run simulations so vast they'd effectively resurrect every possible consciousness that ever existed. In this view, the cosmos isn't just a stage for life. It's a self-repairing archive ensuring no thought, no experience is ever lost. The implications for hidden structures are profound. If the universe is destined for an Omega Point, then the cosmic web's filaments, dark matter's gravitational scaffolding, and even quantum fluctuations might be more than random artifacts. They could be the early blueprints of a system designed to optimize complexity. Some interpretations even suggest that the fine-tuning of physical constants isn't accidental but a prerequisite for this ultimate convergence, like a lock engineered to fit one key. The universe's architecture, from the largest superclusters to the tiniest particles, might secretly be a neural network in its infancy, slowly wiring itself toward sentience. But how could consciousness saturate the universe? Tipler's answer borrows from quantum physics and cosmology. At the Omega Point, the collapsing universe would approach infinite density, allowing information processing to become instantaneous and omnipresent. Every particle, every vibration of light would become a node in a cosmic mind, with the entirety of existence functioning like a single thought. It's as if the universe, in its final moments, wakes up and realizes it's been dreaming itself all along, a self-aware monad echoing the philosophical visions of Teilhard de Chardin, who first coined the term Omega Point in a spiritual context. Critics dismiss the theory as speculative metaphysics, arguing it conflates physics with wishful thinking. After all, current evidence suggests the universe is accelerating toward cold, empty expansion, not a fiery collapse. Yet supporters counter that our understanding of dark energy is still in its infancy, and future discoveries could upend today's models. They also point to eerie parallels between Omega Point predictions and quantum immortality theories, where consciousness somehow persists through all possible branches of reality. Whether prophecy or poetic fancy, Omega Point theory forces us to confront the deepest questions. Is the universe indifferent, or is it, in some unimaginably vast way, alive? Are we mere flickers in the cosmic dark, or the first sparks of a flame destined to engulf everything? The answer might lie hidden in the universe's architecture, waiting for us to decipher its silent, sprawling code. From cosmic webs stitching galaxies together to white holes violently spitting out matter, these 30 theories have shattered our assumptions about reality's hidden blueprints. We've wandered through dimensions curled tighter than threads, stood at the edge of black holes that might birth entire universes, and glimpsed the eerie possibility that we're living in a simulation, or worse, a Boltzmann brain flickering briefly into existence. Each idea peels back another layer of the cosmos, revealing structures more bizarre than fiction. Dark matter's invisible scaffolding, time crystals ticking without energy, and neutron stars with hearts of quantum diamond. Even the fabric of space itself might be pixelated, a hologram projected from some distant two-dimensional edge. What ties these theories together isn't just their strangeness, it's their defiance of limits. They dare us to rethink gravity's rules, time's arrow, and the very nature of existence. Maybe the universe isn't a lone, accidental expanse, but one of countless membranes in a multiverse, or a self-correcting system fine-tuned by unseen hands. Perhaps what we call reality is just the surface of something far deeper, a shadow cast by geometries we're only beginning to trace. Now it's your turn. Which theory bent your mind the most? Do you think we're hurtling toward a big rip, or is the cosmos secretly a time loop, replaying forever? Drop your thoughts in the comments, and if you're hungry for more cosmic mysteries, hit subscribe. The universe is brimming with puzzles we haven't even named yet, and the next revelation might be just a click away. Until then, keep looking up. The stars are only the beginning.